Quem que flecha o bala?
Hi, everyone.
Hey, kela ke kichi pile kamada. Ike kumana gati ya spend uma doesn't go to
Michael, can you hear us? Michael, can you hear us?
Sure.
Hello, Michael.
There.
Hi.
Good afternoon.
Sorry about the delay. We finally got in.
Hey, it wouldn't be a Zoom webinar without some technical hiccups at the beginning.
Thanks for your patience, and thanks everybody else for your patience as well. We did finally get there. People are still joining, so we'll give it another minute or two.
I haven't got my camera on, so they can't see me.
Oh, I think we want to see you at the start, Michael.
And then I will lose, what's his name? Contact.
Okay, we've got a wonderful lineup of people participating so far, but people are still joining. So just hold on just for another minute or so, and then get things started. Michael. I haven't seen Martin yet. I don't see him in the list. Might be going to be a little late joining. But if, Michael, if Martin doesn't join us, as you know, I have to leave a little bit early because I have another seminar that I have to coordinate. Perhaps you wouldn't mind managing the questions by yourself, if that's okay?
Sure, can do my best.
I will attempt to make you a co-host. God knows how that works. Where are you? I think I've done it. Brilliant, you're now co-host.
Fantastic. Let me see if I can share my screen. That'll be the real test.
Yeah. Fantastic.
That seemed to work. Great.
Okay, well, let me say first that thanks everybody for joining us. We still have a little bit of background noise. I think someone's having their tea. So please do switch off your microphone unless you're Michael or you want to ask a question. Welcome. It's great to have you all with us. It's my pleasure to introduce Michael Evans. As you know, we have the singular privilege as editors of the 3 Conservation Society journals to identify papers that we think are particularly useful, relevant, effective, beneficial. And it's my pleasure to introduce Michael Evans. He's a conservation data scientist with Defenders of Wildlife based in Washington. And Michael will correct me if I get all of this wrong, but he
Good so far.
Good so far. Background in Ecology and Evolution and Behaviour, University of Buffalo, and a BA from Oberlin College, as well as a PhD in Natural Resources from the University of Connecticut. And he's that rare beast, a conservation data scientist, and one of the new brand of conservation scientists, of which we need many, many more. And the particular tool he's going to introduce today is one that I think is especially valuable and will be over the next 10 years or so, especially as these tools evolve and the data improves. But Michael, thank you very much for joining us. Thanks for writing the paper, first of all. Secondly, thanks for sending it to Conservation Biology. And finally, thank you very much for doing this presentation for us. Looking forward to it, and enjoy the time.
Yeah, I will. Thank you for that wonderful introduction. And yeah, thank you for accepting the paper. As I will touch on later, we, at Defenders of Wildlife and in the role that I'm in, are really interested in developing applied solutions to tricky conservation challenges, and having some of these methods out there and documented in the literature is a fantastic backstop and way to justify to regulatory agencies and anybody that needs to hear it that they can use these tools for good. So yes, let's dive right in. Thank you everybody for joining. Good morning, good afternoon, good evening. I know we've got a diverse audience in the session here. So I'm gonna present a little bit of the results from the paper that was mentioned, supporting habitat conservation with automated change detection in Google Earth Engine. And I'm gonna try to do this in a way that hopefully straddles a level of detail that's both accessible in case there's folks that aren't real familiar with Earth Engine or using satellite imagery, but I know many folks on the call will probably be very familiar with this technique. So hopefully there will be something interesting for everyone. So a bit of an outline here. We're going to kind of go through the typical academic type background, methods, and results. But I'd also like to spend some time at the end of the talk looking at how we have and think we can apply the results and methods that we developed as part of this paper in the real world, and some next steps for this type of work. So very quickly, a brief background. As was mentioned, I am the Senior Conservation Data Scientist at Defenders of Wildlife. For those that aren't familiar, Defenders is a US-based national nonprofit and focused on protecting native plants and animals in their natural communities. We primarily focus on North American species.
I'm on a webinar.
If I can, yeah, just remind everybody to please mute themselves as they join. We're still hearing some background noise. Thank you. Yeah, so our focus is North American, and a lot of the content that I'll present has to do with US conservation policy. So to begin, I want to take a step back and talk about the motivation for this work. As I'm sure everybody here is familiar, despite a lot of apologies, I'm not sure how I got muted. So beginning with the motivation for the paper, despite the presence of many strong conservation laws in different countries around the world, I'm sure a lot of folks on this webinar are familiar with the fact that natural areas and species populations continue to decline. This continues to be a problem. And so there's a disconnect in our minds between the policies that exist to provide protections for biodiversity and for natural places, and the actual implementation on the ground. And one of the biggest weak links in our view is inadequate monitoring of these conservation laws and agreements. And so to take a US example, there's many laws on the books in the United States that protect species and habitats. The National Forest Management Act requires the US Forest Service, for example, to develop species management plans and manage their lands for multiple use. Probably none of the laws is as far-reaching as the Endangered Species Act, and that's the focus of a lot of our work at Defenders, is understanding how the ESA is implemented and provides protections for imperiled species. And there's really two means that are kind of relevant to the work we're going to talk about here. One is all of these laws often have some sort of conservation agreement where regulations are set forth saying what is protected and what can be developed or what habitat can be removed. And then the second element to a lot of these laws are status assessments for these species, trying to keep track of what the state of their populations and habitat are. And so I mentioned the Endangered Species Act because it is, as I said, will be the kind of the context for a lot of the examples that I talk about later. And the reason for that is it's a very far-reaching law in the United States that basically requires all sorts of federal agencies and private actors to make sure that activities that they're taking are not harming species that are protected on the list, the endangered species list. So it touches all sorts of activities from cattle grazing allotments to irrigation dredging, forestry, fisheries management. it is sort of the nexus by which the US has the most ability to protect endangered species. But as I mentioned, there are thousands of these types of conservation agreements in place under the ESA with really no ability to monitor them. And so I'll start with an example of one of these that kind of motivated this work. The Langboard HCP, which stands for Habitat Conservation Plan, was an agreement for, I believe it was a plywood manufacturing company, to build a new facility in the range of the protected indigo snake. And the basic deal is that the Langboard company could build their factory as long as they protected certain parcels on the property for snake habitat, which are some of the colored units you see. And so this agreement's in place and in principle provides good protection for species. But we were able to follow up, this was many years ago we did this analysis, and just using old school Google Earth images discovered that lo and behold, one of the areas they were supposed to be preserving for habitat was in fact being developed. And so this may seem like a small and relatively trivial example. It's not all that much habitat we're talking about, but in aggregate, considering that there are, as I mentioned, just for the Endangered Species Act alone, thousands of these types of agreements in place, and agencies have been historically handcuffed by a lack of funding and sometimes lack of political will to enforce them, this gap really becomes a key place for sort of a death by 1,000 cuts situation, where you've got lots of these little violations that nobody's looking to make sure our laws are being adhered to start to add up, and we can understand why species are still in decline potentially. And so for conservation laws to fulfill their promise of protecting species, we feel that we need monitoring plans that are three things. They have to be spatially extensive. They have to be able to cover a large area. Historically, that's meant trying to send people out to all these places, and that just doesn't work. They need to be regular so that bad actors don't slip through the cracks. And ideally, they should be passive. And so this is what brings in the abundance of satellite imagery that is now available to many researchers and conservationists' fingertips. The availability of sometimes free and frequent satellite imagery of the entire Earth kind of checks all those boxes as a potential for really powerful monitoring tool. And further helping this, it was the arrival of Google Earth Engine, a platform that has made all this data publicly available and provided cloud computing resources to analyze it, which really increased the access to this data, and is what we used in all the remote sensing and analyses of satellite imagery that you'll see as I move through the talk. So for this paper, and to address this challenge of inadequate monitoring, we settled on trying to develop approaches to automated change detection. So we want to be able to use satellite imagery from two different times and automatically identify places that have changed, and specifically places that have experienced some sort of land cover transition. So if we have an image like this, a before image, an after image, these are all oil and gas drilling pads in sort of an agricultural mix. We want to be able to automatically flag all the places where something has changed. This checks those three boxes. It's extensive, it can be done regularly, and it's passive. Nobody has to go out in the field and do these sorts of things. And so the general approach that we took was sort of a 7-step process. There's lots of other approaches to change detection that have been developed, and we build on a couple of those methods, as I will describe here shortly. But so we focused on this sort of workflow. First, collecting all the images from, in this case, the Sentinel-2 remote sensing system from a given area of interest. Processing those images, meaning trying to mask them for clouds, shadow, and terrain effects. Then dividing that process collection into a before and an after set of images around the date at which we want to analyze whether change happened. Create median composites, so those before and after collections get reduced down to single before and after images, at which point they are run through some sort of change detection algorithm to create metrics. these metrics need to be converted to a single change score so that we can then apply thresholds and say, these are the areas that changed, these are the areas that didn't. So that's the general workflow. And so just a bit of detail on the two algorithms that we decided to implement. We modified them a little bit, but they're based off of work by Jin et al. That published a paper in 2013 describing methods to update the national land cover data set in the US, and this multivariate alteration detection algorithm developed by Nielsen. So the idea behind the LCC algorithm is we've got 6 metrics that sort of summarize on a pixel by pixel basis the magnitude of change between a before and after image. So in these equations, the notation here, B1 and B2 are bands from image 1 and image 2, and I denotes just whichever band that is. So there's the 2 metrics at top that sort of just look at this vector of changes on a bandwise scale, one of which adjusts for sort of the magnitude of the value of those bands. And then we have a number of the normalized spectral indices in which we're taking the difference between image 1 and image 2. And so the output of this algorithm is a 6-band image containing these 6 metrics, which we then normalize spatially by the mean and sample standard deviation of the area. And this is important because we then are able to identify changes that are relatively high anomalies relative to their surrounding area. The MAD algorithm is intriguing because it sort of takes care of this normalization inherently. It uses an approach called canonical correspondence analysis, which you can think of as like principal components analysis, but that maximizes correlation between 2 sets of variables. And so because it's transforming the variable space, this sort of standardization in the area is taken care of. And it produces 6 canonical variates, shown here, V1 through V6, and can be summarized on a pixel-wise basis conveniently with the chi-square statistic. So again, just to kind of reiterate this in more visual terms, the way that we're identifying changes, we've got our before and after image. Those get fed into either the LCC or the MAD algorithm, and we tested both in this paper. And those produce a multispectral output, a multi-band output that contains different metrics indicating the strength of change at each pixel. And then the way that we reduced that multi-dimensional information to a single change probability was using linear discriminant analysis to try to come up with a single change score that we could threshold. Now, to do that, we had to collect a bunch of data from this multi-dimensional output. And so we did that by generating a training data set from many different locations across the US. We found 100 areas where we could observe some change happening, again, change being land cover loss or habitat loss, land cover transition related to habitat loss. And we did our best to distribute these in a variety of habitat types. We wanted to develop an algorithm that was fairly generic and could be applied across many different habitat types, especially given the sort of disproportionate amount of work that has been done to quantify changes in forests. There's lots of other ecosystems that need monitoring. So this generated a little over 1,000 polygons where we delineated changes happening. We sampled the pixel values from those algorithm outputs within each of those polygons, and then also generated 1,000 random pixel samples at each of these locations, and split this into a training and testing validation, training and validation sets, which we then used in our linear discriminant analysis. So using that training data, and those are those change output values from each of the study sites, we conducted a linear discriminant analysis to identify a transformation that changed those metrics into a single change score, and basically used an area under the curve ROC analysis, which you're seeing here, to identify the optimum threshold. So the lines, for those you aren't familiar with ROC curves, are basically showing for a given value of the resulting single LDA score, what's the trade-off between the true positive, true changes you're detecting and false positives. And so this was useful because we were able to use the ratio, the value of the score at which the ratio between true and false positive was highest as our threshold for delineating changes. I'll go back for a moment. So this sort of concluded part A of the analysis. You know, at this point we had two algorithms that were generating change probability images. And this analysis here, given our training data, was indicating that they, in theory, were performing very well at discriminating between areas that have changed and areas that haven't changed. The indicator of that is the area under these curves, which for each combination of habitat type to disturbance were all over 90%. So we were very happy with that performance and decided it was time to actually apply them to some case studies and see how effective they could be in a real conservation context. So we selected 4 areas, and the reason we chose these areas was we wanted to find 4 different cases that represented different scenarios where we thought automated change detection might be useful in conservation. And so those were a small area in Wright, Wyoming, which represented sort of small scale ongoing changes to habitat that we might want to detect. A larger area down in the Permian Basin of Texas, that's sort of a retrospective analysis, trying to quantify past changes that have happened. Panama City, Florida experienced Hurricane Michael coming through several years ago, along with much of the southeastern coast of the US. And so this represented a case where we might be able to use change detection to rapidly assess the status of a habitat following a natural disaster. And Gulf County, Florida is the site of an ongoing deliberation to develop another habitat conservation plan for the endangered beach mouse. And so this represented a case where you've got a small scale sort of retrospective analysis to see what the status of loss has been over time. So in each of these case studies, we ran both the LCC algorithm, the MAD algorithm, and then we also had someone manually delineate all the changes that they could identify so that we could compare the outputs from each algorithm to what a human could do, basically just staring at the imagery. And so these are a snapshot of those results. This is one of the figures from the paper. And so as you can see, the manually delineated changes in blue in that top row really closely correspond to the changes that were identified by both the LCC and the MAD algorithms. There's a little bit of discrepancy in terms of sort of how precise each of those algorithms are relative to the manually delineated changes. But overall, they indicated a strong ability to identify real habitat loss and not identify too many spurious changes. Some other important takeaways here are that for each of these study sites, the algorithms took less than an hour to run, whereas human going through and manually trying to delineate all the changes took, in some cases, several days, and in every case, at least several hours. So there's a trade-off here, and we think this is particularly important for the application of these techniques, is that they're huge time savers and can be run automatically and passively. So I mentioned that we wanted to compare the performance of the algorithms to those manually delineated polygons, because what good is it if we're saving time if the results are all wrong? And so what you're seeing here is the complete raw output from the LCC algorithm in that Permian Basin study. So we've got a matrix of sort of shrub scrub habitat with some sand dunes, and all the black polygons and lines you see are the places that the LCC algorithm flagged as change. And so there is some post-processing that has to be done here. Basically, you know, there are some spurious single pixels, if you look at this hard enough, that you'll see that aren't changed, because the algorithm runs on a pixel by pixel basis. you're going to get some noise speckled in there. And so one of the ways to determine what an appropriate threshold or a way to filter that is to determine an appropriate threshold for the size of polygon you want to consider change. And so we did that exercise for each of the 4 study areas, looking at different thresholds for minimum sizes that we would keep in the output set. And so that's shown in that leftmost column. So a minimum size of 0 means we kept all those polygons. And we calculated 3 metrics: Jacquard, or intersection over union, so how well did the polygons overlap with the manually delineated ones, and then commission and omission rates. And using this, we were able to identify for each case study and for each algorithm sort of an optimal minimum size to keep in our output change polygon data set that delivered a balance of both detecting real changes and omitting false positives. And so using those thresholds, the last thing that we present in the paper is just an example of the ability to really quickly calculate, map, and summarize the amount of habitat loss that happened between 2 different time periods at a given site. So this table summarizes both of the dates of the before and after imagery for each of these case studies, their size, and then the amount of area that was detected as lost as measured by the LCC algorithm in this case. So one of the things that we're quite pleased with how this is working is we covered a variety of different habitat types, which was one of our goals from the outset, was to not only be effective in places where you've got forest transitioning to bare ground, but also places where you've got sand being cleared, or scrub, grassland type habitats. And the algorithm performed pretty well in each of those cases. So at this point, I'd like to shift the focus from kind of what we presented in the paper, methods and the results there, although I'm happy to talk about that too in the questions when we discuss afterwards, and talk about or present a couple examples of how we've actually used these methods now that we've developed them in practice to affect conservation outcomes. So the first example actually is related to the one case study that I've been talking about in the Permian Basin of West Texas. So this is a place where there's a lot of oil and gas drilling activity. It's also the home of the dune sagebrush lizard, which is the most imperiled reptile in North America. It only lives on the dune system in that small region. And in 2016, we got tipped off that there might be a new type of development moving in called sand mines. So in this satellite image, while you can see a checker spot of small oil and gas drilling pads, sand mines are these much larger features that are basically like the mountaintop removal equivalent for sand dunes. And oil and gas companies use these to literally mine sand to use in fracking operations. And this was relevant because the lizard had been protected under a voluntary conservation agreement with the state of Texas that there was very limited ability to monitor and enforce. And so we used our change detection algorithms to automatically identify over a series of months in 2017 the development and expansion of these sand mines. So that's what you're seeing here in this output. The black and white image is a change probability output from the MAD algorithm. And you can see it's flagging things like roads, new little well pads, and those are all covered under the conservation agreement. But sand mines were a new type of disturbance that hadn't been considered. There was no regulations for them. And so they were popping up in areas where the lizard's habitat should have been protected. And so we were able to use this information to first negotiate with the Texas comptroller to try to revamp that conservation agreement for the lizard to accommodate protections in exchange for these new developments. But ultimately, as you can imagine, some of the players down there in the energy industry weren't keen to sign up for a new voluntary conservation agreement. And so ultimately this information, the data that we collected in terms of the area that was being lost, was submitted to as a petition to get the lizard protected on the endangered species list. And over this past summer, we actually had a positive 90-day finding, which means that the Fish and Wildlife Service found the species was warranted, there was sufficient evidence presented, and they're going to move forward with considering it for listing. Really quickly, in a somewhat similar case, we also wanted to analyze anthropogenic habitat loss in the range of the lesser prairie chicken. So this is a small grouse species that's native to the southern Great Plains in the US. And it has an interesting history in terms of its conservation protections. It was actually listed as threatened in 2014, but then taken off the endangered species list in 2016 on account of the fact that, again, there was another voluntary conservation agreement put in place. And this conservation agreement specified, again, areas that could be developed, areas that couldn't be developed, and was supposed to provide a balance of opportunities for energy development while also leaving protections for the bird. And as the story is getting repetitive now at this point, there's limited ability to go out on the ground and make sure that those regulations were being complied with. So we used our algorithms to assess habitat loss due to anthropogenic development throughout the range of the prairie chicken between when it was delisted and now. And again, we're able to supply that information to the Fish and Wildlife Service, and they are currently in the final phase of a species status assessment to consider replacing this species on the endangered species list, so increasing the protections for it. So we're really cautiously optimistic and encouraged by the outcomes of those two case studies and the ability to potentially use automated change detection and satellite imagery to improve conservation outcomes. But we think that the real power of these methods is in democratizing them. Sort of the equivalent in my mind is just like the democratization and accessibility of satellite data in and of itself sparked this huge proliferation and revolution in how ecologists and conservationists are able to analyze landscapes. We think that putting these types of algorithms in the hands of more than just one organization, certainly, could be transformative to how we monitor for conservation compliance. And so along in that spirit, we've been developing an app that is public called Habitat Patrol. We mentioned this in the paper. And this is an app that basically lets anybody with or without remote sensing experience come in and run the LCC algorithm in an AOI of their choosing. It's in a beta version currently. We have to work out some kinks with scaling to bigger areas, but for small AOIs, it works fairly well. And so I'll give you a little demonstration. So this is the app in action. You can see a user comes in, and in this case, they're interested in perhaps finding some habitat loss in your right Wyoming. So you draw your AOI as a user, select the date ranges that are going to define your before and after period. So when are you looking for changes? And then hit run. And as long as your polygon is small enough, we run the algorithm in the background and serve up the before and after imagery. So you can also choose, or you can then select and look at what are the places in purple there that were flagged as change. So here's the before image, here's the after image. And here's all the spots that the algorithm flagged as change. So anybody can come in and use this tool to quantify basically change up to the present, depending on what you set your dates at. And we'll be adding a function shortly to allow users to export those polygons. Let's skip over that actually. So next steps, the applications we think for this technology are many and potentially really powerful. And we're already thinking about how to improve the algorithms. And so where we are going and where we think the kind of field of remote sensing and conservation is going is towards applying computer vision models to this data to improve those algorithm results. And so some folks may be familiar with the sort of integration between one of the deep learning neural network libraries out there called TensorFlow with Earth Engine that allows analysts to basically somewhat easily move satellite imagery from Earth Engine into an environment where they can train deep learning models on it. And the appeal of this to us is that these computer vision type approaches, like the UNet model that I've highlighted here, are no longer operating on a pixel by pixel basis. So where we saw some noise and needed to make some decisions about like where we were choosing thresholds of what change polygons to consider with the earlier algorithms, in theory, a computer vision model is actually looking at the spatial context, the shape, all sorts of spatially explicit information about every patch of the image and making a decision about whether it thinks that is a change based on not only that pixel, but the surrounding area. So in theory, this gives us the ability to develop models that are going to learn to identify human features, basically human change features, and not just determine like, does this pixel look different than it did before? So this is where we've been headed. We have some models trained already using the same training data that we generated for the paper. And as I mentioned really quickly, I think the advantages of this approach are that deep learning models are going to be more robust to clouds and terrain. So you can potentially run the algorithms on a greater range of images. Don't have to be as worried about processing clouds. Fewer spurious pixels, and also importantly, they can eliminate habitat specificity. So a deep neural network or computer vision model should in theory be able to identify human change sort of regardless of the context, provided it's been given enough training data from enough variety of scenarios. And so some early results, these are two sites that we've been testing out. We've got before and after images. And so here you can see the outputs of the computer vision based change detection. And it looks a little different. Granted, this is a very limited sample than the pixel-based algorithms that I was presenting earlier. You don't have sort of these spurious single dots of change. You can see that what the model's identifying are anthropogenic looking shapes, basically, which is exactly what we want it to be able to look for. And one more example to illustrate this idea of really increased generality to habitats. Here we have a mixed landscape where you've got patches of forest, I think some chaparral, this is in California, and then a whole bunch of obviously urban suburban development. And the computer vision model picks out down in the bottom left corner there, a lot that's been cleared and looks like some area to extractive practice in the center that's experiencing some new clearing. So we're really excited and encouraged by these early results. And our ultimate goal is to develop models that can complement, if not replace, the earlier ones that are running in Habitat Patrol. So ultimately from here, next steps, as I mentioned, we are focused at this point on trying to democratize change detection. We want to try to put it in the hands of as many people as possible, the public, other conservation organizations. Habitat Patrol is one way to do that. We're also looking for other partners that have access to different audiences. And we're also really strongly advocating for agencies that have regulatory authority to use these tools. I started this talk saying that these agencies have a lot of legal responsibility and power, theoretically, to enforce positive conservation outcomes. And historically, they've sort of lacked the tools and resources to do it. So if we can put the right tools in the hands of those that have the actual power and authority to affect those changes, we're really encouraged and optimistic about what sort of benefits that could generate for biodiversity conservation. So with that, yeah, I really appreciate everybody joining today to to say and your interest in the paper. And I think we've got time for some questions now, if there are any.
Thanks. Yes, thanks, Michael. So I'm Martin Strauss. I'm from the University of South Africa in Johannesburg, and I apologize for being late. I had some connectivity issues, but I'll be handling the questions for you, because Mark Bergman had to check out to join another seminar. And so we've got a question here from Mark Bergman just before he left. And he said, wonderful presentation, thanks. The ROC stats were very good, but do you consider a machine learning approach, say Maxent?
I think, yeah, so it's something that's a good question. It's something we considered in the early development of the model. And I think what ended up happening is we basically leapfrogged over some of those, I'll call them traditional machine learning approaches like random forest classifiers or Maxent to these neural network-based computer vision models like UNet. I'm at a guess, yeah, I would say that some of those machine learning approaches probably would be an improvement over the LDA approach that we took. But at this point, we're fairly convinced that, yeah, the neural networks are the way to go in the future, because we can actually identify like shapes and features and not just pixels.
Thank you. Then we have a question from Claudia Schuner, who says, theoretically, could this also work the other way around? In other words, observing the restoration of a conservation area?
Yeah, that's a great question. And it's one that I often get when sharing this work. And so theoretically, the answer is yes. As the models are formulated, they're not specific to loss per se. We trained and developed the parameters for the LDA discrimination analysis based on identifying loss. So the adaptation that would have to be made is one would have to basically collect examples of the opposite process of restoration and just come up with another set of parameters for the model to identify that reverse case.
Thank you. Then we also have a question from Francisco Reina, who says, can the before and after and change images be exported, say saved as a GeoTIFF or something similar?
I assume that that's in reference to the Habitat Patrol app that I was talking about. We don't have export functionality right now, but it's the next feature that we're going to be adding. We're working on sort of version 2.0 of Habitat Patrol, and being able to export the images, the change polygons, and then potentially a report sort of summarizing the findings and the parameters that were used are new features that'll be coming.
And a question from Brian Cohen is, can a user upload a shapefile or other format and run multiple requests?
Users can upload shapefiles. We're also adding the ability to query the Fish and Wildlife Service's database of species ranges. So if you don't have those shapefiles on hand, they can be pulled in and change detection run within them. The current limitation, I think, I don't think multiple queries are possible, is that the calculations all still have to go through the Earth Engine server, and they will occasionally put throttles and bottlenecks on how large the computation that's being requested can be.
And a message or question from Claire Relton. Does your Habitat Patrol work in other parts of the world outside of the US? Was it still only US based?
Yeah, good question. We would love for someone to test that, actually. There's nothing that would stop a user from running it outside of the US. We're most confident in running it within the US just because that's where the training data was generated from. But yeah, someone could try it wherever they want in the world. I think my guess is it would probably work pretty well in other forested or grassland, similar ecosystem contexts. I don't think it would do particularly well in the Arctic, let's say, just because the model hasn't seen any examples of ice or snow.
Claire Relton says she'll be happy to test it for you in Southern and East Africa.
Fantastic.
I don't see any other questions in the in the chat at the moment, but I
Okay.
was wondering, to date, what's the uptake been on the app?
You know, I would have to ask one of our developers who's been tracking the metrics of use. It's fairly new, and we've sort of been softly introducing it to folks. So I'm not actually sure how much it's been used. The one encouraging, or sort of the most encouraging metric that I can share is that we have shown it to the Fish and Wildlife Service, and they've expressed interest in possibly adapting, if not this app, the methods in some of their official monitoring processes, which would be a huge conservation win from our perspective.
Okay. Another question from Claudia Schöner is, could you use it to look for habitat change in water or the ocean, like oil spills or plastic?
I think it would be ill-suited to those situations just because of the spectral differences in water. I would instead point you to colleagues at a small organization called SkyTruth that also does a lot of remote sensing work. And they've been doing some really cool stuff with SAR, the radar reflectance data, to detect oil slicks specifically that are either leaking from like old oil platforms or ships that are docked just offshore. So they've got some really cool products that, if you're interested in the marine context, I would point you towards some of SkyTruth's work.
Okay, and maybe one more from me. I mean, are you using this in any sort of further work that you're conducting at the moment, further research?
Currently, yes. So I mentioned that we just submitted data to Fish and Wildlife Service for the lesser prairie chicken, and so we'll be publishing a report on those findings here shortly. We're actively monitoring one of the case studies that I highlighted, which was the case of the, hold on, I can go back to the slide. So the Gulf County case down in Florida, that's a situation where there's been ongoing residential development while the county has sort of delayed finalizing some sort of protection agreement. So we're continuing to gather data there to hopefully put pressure on them and the federal agencies to put some protections in place. In terms of ongoing research too, the other thing I wanted to flag that I forgot to mention is that we have made, and as we collect more training data, we'll continue to make both the polygons and the pixel values that we've exported publicly available in an OSF repository, which I flagged here. So, you know, if other folks want to take that and come up with their own approaches to detecting changes, and if that could be valuable in any way, yeah, we want to share it and see what everybody can come up with.
Okay. And then another question from Brian Cohen. How dependent is the methodology on multispectral data? Could it be modified to use higher resolution but only 3-band data, i.e. NIPE?
Yeah, that's a great question. It could really be really easily modified. And that was one of the motivating factors for choosing the algorithms that we did. Both LCC and MAD are you know, agnostic to what data they're given. The only exception there is that some of the spectral indices like NDVI, NBR that are used in the LCC algorithm would not be possible without some of the shortwave bands. But otherwise, yeah, you just need, for LCC, you just need 2 images with the same set of bands. The cool thing about the MAD algorithm, and we've tested this out, is because it uses canonical variates, you don't actually have to even have the same number or types of bands in the before and after image. So that one is quite flexible in terms of what inputs you give it.
Okay, and then I see there was a question on where can one access the tool if one wanted to download it, and I see Brian Cohen has shared the link. So thanks, Brian, for sharing that.
Yep, it is a, yeah, so we're hosting it as a web application. I can also share in the chat, maybe we have a GitHub repository that hosts the source code if folks want to, yeah, play around with the methods locally.
Okay. No, I don't see any other questions in the chat. We'll just give it a minute to see if any more filter through. Maybe while we wait for that, I can maybe just highlight that on the 10th of March, we will have our next seminar at 10 GMT by Diego Cardeñosa, and that is on Indo-Pacific origins of silky shark fins in major shark fin markets, highlight supply chain and management bodies key for conservation. And no more questions have come through. So I think we're just about on the hour as well. So with that, I'd like to thank you, Michael, for your time and for your interesting presentation. Yeah, we look forward to see the uptake of Habitat Patrol. And there's just a question for the link to the GitHub repository, if we can get that in the chat.
Sure, I can throw that in the chat right now.
Maybe you can just post that for us before we log off.
Absolutely. Oops. Okay, that's just been shared.
Thank you, that has come through. So yeah, thanks again for your time. And good luck with your work. And thank you everybody for attending. And please join us again on the 10th for our next seminar. Thank you very much.
Thank you.
Thanks, Martin.
Bye.